أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم السلام عليكم ورحمة الله. This is the second part of our electrostatic chapter 2 lecture 7. So here we will learn about in the last lecture we learned about electric force and electric field, how they generate and what is the relation between these two. Today we will learn one more entity which is called electric flux density. So which is D, we are denoting electric flux density with D is equal to epsilon naught E, which is this one. So if you multiply with epsilon with the electric field intensity or electric field strength, you will get the electric flux density. But what is this electric flux density? This is actually comes from Faraday's law, where Faraday actually made one experiment that he have taken two different size of spheres and he put one into another. Means the smaller sphere, this one, he put inside a bigger sphere, and then there is a gap between them, which is vacuum. So there is nothing here, so we call it free space. We call it vacuum. So what he did is he put one positive charge in the outer surface of the smaller sphere, and then after that he observed that the same amount of opposite charge is actually inducing at the bigger at the outer surface of the bigger sphere. So he was wondering that how it can be possible. So he put up a theory that there might be some entanglement or some connection between the positive and negative charge that is attracting each other. He have named that attraction or the pathway of attraction is electric flux. So, or they sometimes call them electric flux lines, which is directly straightly it goes towards the from negative charge from positive charge to negative charge. So if when he tried to this actually let me go back again to the electric flux line. Is these lines are actually invisible lines, which is called imaginary lines. We cannot see it, but we can feel it. We can feel means that this actually defines the strength of any electric field. As much as electric flux you can generate means you are actually generating as much as the electric field strength or intensity of the electric field. Now when you place so many charges, many as infinite numbers of charges, then it will produce the infinite number of electric flux lines, which will, if it's positive, then it will go outwards, and if it's negative, then it will go inwards, because this is negative, right? So it will have an incoming flux towards it, but for all the positive ones it will go an outward flux lines. Now he said, Faraday said that the total number of flux or the flux line is equal to the number of charges. Means if there is one charge, you will have one flux line, and so on. So he said that the total flux is psi is equal to QT, means the total number of charges. Now from the density we can say that if it's usually we calculate it in surface density actually. So the total flux density here is, if we define it D, that we have defined it already actually, D is equal to psi divided by the surface area of the sphere. Means which sphere is located with. So the surface area is, we know, 4 pi r square, and we know that if it's a vector, and it is a vector, we need a unit vector towards r direction. But we know also from this equation here, sorry, I have to go so many, E, that E is equal to Q r square, right, a naught. So we know that. So from there, when we compare these two equations, this is the flux density and this is electric field strength. The only thing that is difference between them is the epsilon naught. Epsilon naught is the property of any medium, means it can be vacuum, or you put oil here, or you put air, or you put wood, or you put water here. So water will define E R of water. So if you leave this one, so this whole equations become actually E is equal to D divided by epsilon naught, because this whole thing is D, right? So that's easily, you know, we get actually D is equal to epsilon naught E. So if you multiply epsilon with any electric field intensity or electric field strength, you directly get your electric flux density. So this is how actually the derivation of this one. I usually don't go so deep inside the derivation, but for the sake of your knowledge, you need to know this one. That's why I try to, you know, make it as easy as possible for you. Now, for the closed surface actually, later on we will know about these things. Closed surface, the total electric flux actually psi, you can, you know, integrate with a closed surface integration, and you know, already we know that if it's a surface integration, then we have a ds, the differential surface area. So we get total number of electric flux. As I told you already, that if it's a positive charge, then all the flux lines, they will go outward. So it will go towards the negative, means it will go outward from the positive charge. And if it's a negative charge, it will tend to come inwards, means towards the negative. That's negative charge. So that's the way actually the electric flux travels, from positive to the negative charge. So there are some definitions, you read these things, and there are some also some comparison. Means if this is point charge, we already derive this E, how it happens if it's a point charge. And then for point charge, this is electric field intensity, and this is your flux density, electric flux density. And for the line charge, the same thing, that how we calculate electric flux intensity, or electric field intensity, and we calculate electric flux density. Just I'm repeating again, there is no difference between them but the epsilon naught. So if you take away this epsilon naught, means if you multiply with E, you will get D. It means if you know E, you multiply with epsilon naught, you directly got your electric flux density. This some text I have put here for you to understand. Later you read, and then possibly you will understand this one. We move on. So the unit of the electric flux density is, since we know that total charge is C coulomb, we say, and then divided by meter square, because it's a surface. Okay. So also there are some, you know, if it's not a closed surface, because before I told you that if it's a closed surface, if it's not a closed surface, then you just make a double integration. That's all. If you make a double integration, that you will get it. But I already teach you how to do the double integration, and if a different coordinate system is given, then how you can choose your different coordinate systems. So this is as simple as that. It's nothing scary, not so difficult to understand. However, sometimes for the calculation sake, it can be very tedious and very long. So that's how you can find the total flux if you integrate surface integration with electric flux density. So we do one example today now here. It says that determine D, means the flux density at a point, vector point is given in the rectangular coordinate 4, 0 means x is 4, y is 0 and 3. If there is a point charge of minus 5 pi millicoulomb at 4, 0, 0, and the line charge 3 pi millicoulomb per meter along y-axis. It means at along y-axis they have one line charge which is containing this much rho L. So this the line charge density, and a point charge is locating at this one. So there will be two different charges. So we will have two different for Q charge and for dQ we will find, and then we will find dL, and then we'll add them to find total D. So we go to the solution, as what I said, that this is the line charge rho L is given along y-axis. If it says that another x equal to 2 axis, so it means here. If it says that z equal to 2 axis, then means it's here. And if it says y equal to 2 axis, means the line charge is going like this. Then you have to make a difference, make a distance from here. Now we have two different charges, different distribution of charges also. Means we have a point charge here and we have a line charge here. So for point charge we will use a point charge equation, and for line charge we will use a line charge equation. Here what we have learned it so far here. So point charge we will use this, and for line charge we will use this. So this will give us dQ and this will give us dL. So here now, so first we try to find the point charge due to the electric flux density due to the point charge. So we know dQ is equal to E naught E, and here we got it. Now this is the same. This is the same thing R that we have calculated for E and F also. How to find the electric flux, electric field intensity and also electric force. So you know how to do it. So I will not go deep into it. So that's how this R, and then directly you can find here minus this one. Now since this is given, so you cannot take minus away, you need to put it there. Okay, so it's the negative direction of AZ, so dQ. So the dQ is at the negative direction. See here, dQ as a negative direction. So since the Z direction is upward, so if anything goes if it's negative, means it's going downwards. Okay, now dQ is done, so we go and find dL. So dL means we know that rho L twice by rho A rho. That's similar way, in the very, very similar way that we have done previously. We'll find A rho means rho divided by rho modulus. So here rho divided by rho modulus. So this is rho vector, this is rho vector, and this is rho value of that rho vector. So that's we got, and we know we can get it from here 5, and then we put dL is equal to this. So we have this. So once we add this with this, we get this value. So that's how you can write any way. You can put it 0.00 some 0.0 millicoulomb, or you can put something coulomb also, no problem, but the unit is coulomb per meter square. Remember one thing, in the exam your unit have to be correct, otherwise some points will be deducted. So if it's electric flux density, then it have to be C divided by meter square. So that's how we solve this one. Now we move on to the Gauss law. So the Faraday law is, we already know now the Faraday law, and now we go to the Gauss law. Gauss law said actually that if there is there is an enclosed surface, we will discuss about this enclosed, what is enclosed surface later on, then the total flux is equal to actually the total Q, which is actually is repetition, kind of repetition. But he added that it can be only sustained, like he has corrected, actually the Gauss have corrected the Faraday's law in a way that the total charge will be equal to the total flux only and only if the surface is enclosed, means it doesn't have a infinite length. So how it can be visualized here like this. See here, this one, this is a loop, right? Anything which have a loop nature, like a circle or like, you know, it can be cylindrical also, but it have to be enclosed, means you start from here and then when you travel back and you come back to the same point is a closed loop, means closed surface. So this is a closed surface. Now if you cut it here, you will get something like this, right? So this means once you start here, you are coming, but you need to come back to the negative direction. To come this point is not a closed surface. Means once you come here and you stuck here, so you know way, there is no way that you are going back here unless you are walking in the reverse direction. It means this is a open surface. So this is the difference between the closed and open surface. So Gauss law have told and corrected a little bit, added, actually I would say, I would not say corrected, he have added to the Faraday's law that the total number of flux lines or flux are equal to the total number of charge if there is a surface, enclosed and closed surface. Now we try to visualize this one. These are the 4 criteria that for the application of Gauss law. I just put it there. If you want to know, you can, you know, put you can read about it. But usually when we apply, this is just a theory. Okay, when we apply with knowledge of our mathematics. That's all. But however, you read this one because this is Gaussian surface. We call it, means like, you know, any closed surface, we call it Gaussian surface. So we will not say closed surface anymore after this. Maybe we will say that this is a Gaussian surface. So you read about it, and later on maybe some question can ask from in the exam or in the test about this also. So read about it. If you have trouble, then you can discuss with me. So for the point charge, you know, it's similar that if it's, we make it a, you know, closed circle. If it's a closed circle only, then we can apply it. If it's only a free point charge, we cannot. So we make it a closed circle, means it's a Gaussian surface, we make it, and then we apply the Gaussian law, Gauss's law. So the Gauss's here, so the Q is equal to closed surface integration of dx. Okay, and then since we know that d is equal to drar, and here is actually totally, if you do this integration, I am not going so deep inside, guys, okay, because I don't want to. Okay, So if you integrate this, you will get 4 pi r square dr 4 pi r square. From here, if you want to find dr, then it becomes q divided by 4 pi r square r. So this is how, this is the same thing what Faraday says for the point charge, but for the surface it's a little different. So when it's a line charge, infinite line charge, so you want to find what is going on in the infinite line charge, but you cannot calculate it for the infinitely. So what you have to do, you need to define a closed circle, which is L. So once you define a closed surface, which is Gaussian surface now, because it's enclosed, right? It's have a circular surface. So only we'll find from here to here, which is rho L is equal to total Q, as we know from our previous lectures, and the total Q is equal to this one once we integrate this one, and we got dP is equal to Q divided by twice pi rho L, this one. So from here we this is just to remember that if it's a line charge, then you can directly apply this one, what we have actually have used here in our in the solution here, here. Okay, so it's the same thing, but in a different way actually we are representing. So this is the values here so far that we know about the line charge and the point charge also. It's the same for the Gauss law and also for the Faraday's law. Now we go to the Gauss's law's differential form, means that we will use the divergence operator and the differential form to represent. Okay, this part actually, this is basically theories. Okay, so I would like you to study these theories, understand. Okay, later on we will apply into to solve different problems. So we know about these differential forms already, so I will not say too much about it. So we move on. That the Gauss's law integral form, already we know this, right? And there is one more law, we call it differential form, means if this is gradient, right? Isn't it? We know it, right? So if you gradient means if you do this del operation with the D, means the electric flux density, then you will find the total charge density. Okay, so these are the two Gauss law. Again, this is Gauss law we learned just now in the integration form, and then this is the differential form of the Gauss's law. Don't need to worry about these things too much. I just need to put, if somebody want to explore more, then you can try to explore, but I would not ponder on this too much. Okay, but rather we focus on these two identities, which is Gauss law's integral form and then Gauss law's differential form. So later on actually we will use this one to prove our divergence theorem. Here the D, we are actually learning about all this lecture is all about learning about the electric flux density. So where the total flux, okay, the total flux you can find by total volume integration, means like the individual surface integrations, means this front facing, back facing means at the back. So it's like this, bottom face here and then 6. Okay, so the total charge of any volume can be calculated from all the surfaces belong to that object. So if it's a cube, then cube have total 6 different surfaces, right? So to all the surfaces, if you do an integration of surface integration only, then the surface integration of 6 different faces will add up with a total value of the q charge enclosed by the total volume of the cube. Means the volume integration of ds is equal to actually the enclosed surface integration of that cube, which is actually the divergence theory. But I just put this one here for you to just understand that del operator can be the same operator as we have done it, like v, m or e or f, just the same. So the del is equal to dx, del x dx, del y dy, and del z dz, and these are the other derivations of for the cylindrical and spherical coordinate. Oh, by the way, I forgot to put it here. This is the rectangular coordinate system. But from here actually what we get that the total volume integration is equal to the total different surface integration actually gives us the same amount of enclosed charge. Okay, so this is the repetition, I believe. So this is what so far what I call it here, what we learned actually called the divergence theorem. Divergence theorem says that if there is an enclosed surface, then if you make a surface integration, then the volume integration and the surface integration will give you the same amount of result. Means if we try to find some charges, so it will give you the same amount of charges. So here we actually use the differential form of the Gauss law. How? Here, look at here. So total amount of charge surface q enclosed, we get the total if you integrate surface integration of the closed integral of d dot ds, we get total q enclosed, right, which is actually equal to the total volume charge density dv and then the volume integration, right? But this one, check here, we just learned about these two identities, right? So we know that rho v is equal to del dot d. So once we put here, then we get this one, so which is equal to this identity, which is actually the divergence theorem. However, divergence theorem basically, practically, if you realize, it means the positive divergence theorem means if you do a divergence theorem on any electric field, means the electric field is increasing, and the negative divergence means the electric field is decreasing. So if you do divergence on any electric field, means the field is increasing. I'm repeating again, the field is increasing, means by the divergence theorem you find out how much increase and decrease in the electric field. Here now we are not so far away to finish our lecture. Energy density, the same way we can find it, the W is equal to half of Q V1, Q V2 and Q V3. If there are 3, if it's infinite, then is up to n. Okay, and here for the line charge, this is the integration way to find out the total energy. And similarly for the surface charge and for the volume charge, we do double and the triple integration respectively with the rho s and rho v. And also at the end actually, at the end, as usual, at what I said, that I will not go so deep inside the derivation. It's very tedious and tiresome for you, for me, both. So we will take the equation and we will use it. So at the end of all the long derivation and everything, we get WE, means the total charge by any enclosed, total energy held by any enclosed surface or any enclosed object or any Gaussian surface or object is equal to half of the permittivity, epsilon naught, means the dielectric constant of that material, and the square of the total electric field in strength. So you know electric field strength and you know the property of the material. You can directly calculate how much energy it can store on that surface or on that object. So and at the end, sorry, this is kind of repetition, but it's okay. I will later on delete this one because I just wanted to demonstrate these things to you directly. But this is the derivation. I will not keep give you in the slides. I will just delete this one. And then this is the attendance for the lecture 7. So you determine determine the electric flux density for the point charge and for the line charge given, and you submit by tomorrow. That's all from my side. Possibly we'll have one more lecture on the electrostatic. This is the part 2 of the electrostatic related lecture. So next lecture will be the last lecture on the electrostatic. Thank you so much, and I wish you good luck until we meet again, inshallah. Assalamu alaikum wa rahmatullah.